Thank you, Dean Parkinson. Can you all hear me okay? Good. This is an amazing honor for me to come back here after all these years and be able to participate at this level. It is an honor that ranks as a capstone on my career. So thank you very much, Dean. I appreciate that so much. Thanks to my wife, as you heard with the introduction. Without her, I would not be here. And the family and friends who have come to hear this lecture. I really appreciate them and give them my love. I wanted to talk with you a little bit about my career and a couple of the projects which I'm working on now. But then I want to talk with you, each one of you, each of the technologists, the engineering, be you mechanical or civil or chemical, about what I consider and what my affiliation with the ASCE, what I want to talk to you about is the new kind of engineer that we need as we go forward in this world, because conditions have changed, and I want to talk to you about that. Now, I came last year, and I apologize to Dr. Brown, because I robbed this off of the website. And he presented a talk about neural probes, which helped people who were quadriplegics be able to regain motion again. And as you can notice, this probe on a fingertip. And he was a micro-engineer. Well, I have to tell you, my career went the other way. This is one of our container cranes, and that's me down here. So I decided I would go big, and when I went to the port and saw these cranes, something reminded me of, I don't know what it was, but then I realized that those AT-AT walkers, or however you call them, looked a lot like our cranes. In fact, what I heard is that George Lucas came to the port of Oakland and modeled those after the profile cranes. And so I'm thinking that next year we might invite Yoda at this particular lecture. I know he's not a graduate of BYU, but maybe we can make him honorary. In any case, I'm talking about large stuff, and let me talk about that a little bit. An average container ship, which we get several thousand a year, can supply, like a mall, completely fill that mall 8 feet high with clothing and toys and goods and whatever else. At the Port of Long Beach, this is what we get, is these 8,000 to 14,000 TEU, which means 20-foot, the equivalent unit. What that means is, you see these containers here. These are 40 foot. That means that each of the ships probably will bring in about 6 to 8 to 12,000 containers, and we've got to offload those every year as soon as they come. So let me talk about how large these things are. One of these ships is as tall as the Empire State the building would be, and as wide as a freeway. Anybody recognize the stadium? According to Google Earth, that's how far the distance is. That's how big a container ship is, if it gives you any idea. It is as wide as the I-15 is the parkway out here. So if you're an engineer on the back of the boat and got to walk all the way to the front, you've got the number of steps which you need on your fitness program. These are the kind of ships we get at the port now. And many of you may have heard that the Panama Canal is being rebuilt. Our ships are too large for the canal already, which is a huge advantage and a business advantage to us. The ships are growing, as you can see. In 10 years, they had, in fact, doubled in size. In the next few years, we will be getting 22,000 TEU ships. These things are huge. The scope of the logistics trade will boggle your mind as to how much goods and cargo comes in. And the logistics trade is not, it's not like a hugely technical business. It just requires moving containers off of ships as quickly as you can and moving them over to Walmart. That's really what's involved. So let me talk about a couple of the projects which we're working on to manage these container ships. This is a picture, a recent picture of the Middle Harbor Container Terminal. It will be the world's most environmentally friendly terminal once it's completed because of the use for advanced technology. It's a $1.3 billion investment, and it will manage 3.3 million TEU a year, making it by itself the 4th largest port in the US. So it'll be a huge increase. But the very interesting thing is that from this location, as the containers come off of the ships, until this location, they will not be touched by a machine that is run by human hands. It'll all be computerized. And let me explain that. These are the cranes at the quay, as we say. There will be 14 of these cranes. These are the world's largest cranes. They can reach across 26 wide container ships. The interesting thing about them is they are a dual lift, dual trolley. And let me explain that real quickly. This contraption here will pick up 2 containers at a time. It will lift those, and this is the operator doing this, and bring those containers back here, where another operator will remove the cones off the bottom of the container, which is how they get locked in on the ships. From that point on, this crane operates by computer, and it'll lift off those boxes and drop them on the automated guided vehicles, which will move them from the ships in the stacks and over to the train yard. That will be done by vehicles that have no driver, that they're electrified. This will be completely controlled by an operating system. The interesting thing is I want to be there as I watch this stuff move around. There's not a human on the terminal, except the crane operators. At the stacks, when the containers will come in, will be these stacking cranes, and those will work all day and all night to sort the containers, that in the morning when a truck comes, it will be the first container at the top of the first stack, which means that a truck will enter the terminal and be gone with the load within 1 minute. You have to be as efficient as you can because of the cost of this stuff. This is the kind of construction we're doing out there. I wanted to point out that there's pile driving, thousands of piles, and they're building a wharf on that, and there's the landfill that we are reclaiming all of this land with clamshells as well as with a hydraulic dredging the operation. We're going to move 3 million cubic yards of material to make that fill. Talk about careers a little bit there. I understand there's a lot of women, a lot more in the field now than when I graduated. And you can see there's a lot of careers which I would encourage our women, our mothers and our sisters and our daughters to pursue careers like this, because they are extremely rewarding. Now, if you ever thought that you wasted a lot of time when you were a kid with video games, using the joysticks, just imagine that you could have a job right now that pays over $200,000 a year, and you work like 6 hours a day, basically operating that crane with joysticks. So mothers, be a little bit more gentle on your kids. The next project is the Gerald Desmond bridge replacement. This is a 1.5 cable-stayed bridge. It is the first vehicular cable stay in California. This is the old bridge. I don't know if you can see it well, but all along here are nets, and we call those diapers, because concrete is like dropping off of this bridge. This bridge will carry 15% of the container cargo that comes in the U.S., and it's falling apart. This is what we're going to replace it with. Let me just talk about this a little bit. The old bridge, as you can see here, the air draft, as we call it, which is from the water to the bottom of the bridge on the old one, is about 155. That is no longer high enough that we can transit the container ships. The replacement will be 205 feet, the air draft. I can be on this bridge, and I will be able to talk with the ship operators as they go under the bridge in a normal voice, because those ships are this big. You can see how large they are that we're expecting. The pylons will be 515 feet high. The highest structure in Long Beach. For your geotechs, these are the foundations of the bridge. As you can see, of these the pylons, what you see here are the 10 cast-in drill-hole piles. They are 8 feet in diameter, each one of those. On top of those will go the pile caps, right here. And this is the reinforcing on the pile cap. We just completed the first pour, which was 85 feet by 85 feet by 16 feet high. It's a lot of concrete. These are the approach, the span, the bents, and you can get an idea as to how high those are. So talking about the port a little bit, it's $180 billion of trade a year. When I was at the CE department in January, I asked the students, if you look at your backpacks, look at your purses, look at your calculators, or like in your phones. And if anybody here has one made in America, would you raise your hand? Because right now the global trade is from China. This is what we get from China compared with everything else. What we export is leather, steel, scrap steel, which they use, but 60% of our containers that go back are empty. And so this is a global organization. This is a global undertaking. And you can see here the advantage that we have as the Port of Long Beach, in that with the rail system we have and with the shipping that we have, we can compete with anything that comes around the canal. But it is a global trade, and I want to talk about that a little bit. Not a lot of you were alive when these pictures first came out, but this is a picture of the Earth looking over the moon. It was called an Earthrise. When that picture first came out, and these other ones from NASA, it changed the concepts that we had of the Earth. Previously, we said, or we thought, that the environment would be able to provide us with enough resources, with enough energy, with enough water, and the ability to assimilate our waste and regenerate itself. But this pointed out how limited that Earth was and how limited those resources are. There was always an approach that if we ran out of resources in California, let's go get some from Montana. And if that was a problem, technology would fix it at some point. We would get better technology. Well, let me talk about this a little bit. I want to talk about the Human Development Index, which is, when you look at it, the global scale. This is a measure the UN uses, which is life expectancy, knowledge and education, and the gross domestic product, as a way of looking at a country as to how developed that it is and the quality of life for the people there. And this is how it shakes out. North America, Australia, South America, and Japan have very high standards of living, and much of the world does not. Just keep that in mind. Talk about carrying capacity a second. I think this is a very good graphic about a carrying capacity. In other words, how much can an element carry and maintain? You can look at the Earth this way as well. And the bad news is that as of the early 80s, we were exceeding the carrying capacity of the world. In other words, it was not regenerating quickly enough as it had in the past. And we were now consuming permanently the resources. What this graphic shows is that, as of 2008, we needed 1.5 Earths to be able to maintain what we were doing in a sustainable manner. That can't go on for long. It has to change. So let's graph the carrying capacity, which in this case is the footprint, with the ecological footprint, which is how many hectares is needed to support one person. Okay? That's all the water, all the energy, all the food, the waste, the assimilation, the wood which you need for your house. It's about 1.8 hectares is what you need per person. And this is the HDI. In this area, it's a good quality of life, like we have here. If you map against what the world is doing. The United States is consuming 9.6 hectares per person. That is not sustainable. We can't keep doing that. And you can see that a lot of the underdeveloped worlds, although they are not consuming as much because of their subsistence living, they are also in a very poor condition. So it's all of mankind that we're talking about here. And that's our earthly home. Let me just kind of give you a quote. For the earth is full, and there is enough and to spare. Yea, I prepared all things, from Doctrine and Covenants. Now you're saying, but the Lord has promised us that the earth is all we need. Well, something's going on. Something's wrong. And let me show you what's wrong. This is Olympia, Washington. With a 100-year storm and only 3 inches of sea level rise, the complete downtown gets flooded. Did the engineers do something wrong there? Think about that. This is also Washington. There was a rainstorm before this event where 200% of the normal rainfall fell in 45 days. This earth slide buried a village and killed 43 people. Did we do something wrong? Let's bring this home, look like to this week. South Carolina, Hurricane Joaquin, a 1,000-year storm. 25 inches in 5 days, 11 deaths, 9 dams were breached, and bridges failed. Did we do something wrong? Did we do something incorrect? Or has something changed? This is my home. This is where I live in California. This freeway was rebuilt, the 5, in 2009. That was 9 o'clock in the morning. 5 years later, this is what it looks like. It's one of the 5 worst reaches of freeways in California. Did we do something wrong? Remember, this is at least a 50-year freeway. That investment should be good for 50 years, and after 5, this is what's happened. Did we do the right project? How do we even know we did the right project? Are more freeway miles what we need? Well, things have changed. Here's a graphic that ought to really scare anybody. This is a graph of the petroleum resources, the fossil fuels. And the projection is that the supply will be gone in the mid of the next century. So if you're building a 50-year structure now, what are you counting on for the energy source at the time this gets built and the time that it gets operated? What's happening is that the long-held assumptions that what was the past was prologue in the future. In other words, if we could use the design standards, the averages, the standard deviations, and all of that of the past, we ought to use that in the future and everything will be fine. I'm here to tell you it won't be fine because the conditions are changing. The climate is changing. We have overused our resources. The systems, they are degraded. And social awareness. When I was hired at the Port of Long Beach, I was told, come work for us, it's not a problem, we can build whatever we want because the community doesn't care. They don't even know we're here. We can build whatever we want. After 2 years when I got there, the development of the port was completely halted for 3 years because the community rose up and said, that project that you're doing will degrade our way of life. I don't care about the US and about more cargo. It's going to degrade my kids and their asthma. So communities are now becoming much more involved. ASCE, which I report to, rates our infrastructure as a D+. We are number 23 in the world right now. So what do we need? Let me give you some hope about sustainable development. Sustainable development will combine the three elements of the environment, the economics, and the social, and you can hit the sweet spot if you take all of those into consideration. The current view of the world was that the economy was the most important thing, and that the environment was a dependent upon the economy. If anything went wrong, we would fix it. And society was just there, so to come along on the ride. The problem is, we gotta view the environment as what's immutable. Those are physical laws. We can't change them. And society depends upon that environment, and the economy is what we've invented, what we can control and what we can invent. The engineers, the chemicals, the mechanicals, the civils, the technologists can build the products which support the economy. The civil engineers will build the infrastructure that supports the society. So what is needed is a new engineer that can't be neutral about the environment and about what we're doing. This says that by the time we begin our design, most of the impacts have already been decided. Most of the environmental impacts have already been decided. Another way to look at that is all of the really important mistakes are made on the first day. So we've got to have a different attitude about how we would develop and build products. We've got to think that this earth is not what we inherited from our ancestors, as the Indians of America would say, but that we borrow this off of our children, because they will not have that quality of life if we don't do this. So the challenge is we've got to drive material efficiency. We've got to use concrete and steel and other resources more effectively. ASCE is asking that we reduce the cost of infrastructure by 50% in 10 years. That means better design, less use of resources. The energy efficiency. We are only efficient 10% of what we could possibly be. So we've got to make a difference here. Talking about society, it was where the engineer was the hero, and he could do whatever he wanted, and the public would trust you. In the next few years, it was, I trust you, but something went wrong, let me know what you're doing. Then it was, look, show me what you're doing, because I'm not really sure I trust you anymore. And finally, it's involved me. I'm a part of this process. That means that the engineer must learn how to deal with the community and society and the politicians and the regulators and everybody else who would be involved in a project. We have the technical complexity down. That's not a problem for us. You guys are all learning that right now. What you're not learning in school is about the social complexity which will face you out there. Your projects must be respectful of the culture in which they will serve. Let me give you an example of that. My aunt was a housing coordinator down in Samoa. They needed housing. They brought in Western housing, and they constructed a bunch of Western-style houses. They noticed after a few years the increase in delinquency, divorce, drug addictions, and other things. And one of the things that they traced it back to was the fact that the traditional homes, they were round houses with a pole in the middle. and the father would preside over the house from that pole. They removed that in the Western, the housing and the culture suffered. We have to understand the impact that we will have on the cultures. Remember, we're building 2050 today. What you build in housing can last 50 to 100 years. I live in a house that's over 50 years old right now. So what you build now will be here in 50 years. It'll be your kids' homes that you're building right now. We've got to do it better. We've got to be more respectful of the cultures which we're in, and we've got to do it efficiently. It requires new design approaches. What's happening is that we don't know what the conditions will be in the future. We don't know how much rainfall we'll have. It's not what it was in the past. A sea level rise would be an impact, and we've got to design with that uncertainty in mind, which is hard for us as the engineers because we want precision. You've got to develop new relationships, not just with the owner who you're building a product for, but with the community which will be impacted by that project. It requires a kind of engineer. And this is what we're asking you to do. In your normal planning and development of projects, we normally look at only the end of construction. And if the maintenance guys are lucky, we might consider them in the project. On the environment, we say, do no harm. Do no harm. Just don't hurt the environment anymore. And it's the owner who we deal with. Well, we're asking you, when you design, to think about what you're going to do at the end of the life of that project. Where are those resources going? Where's the concrete going? Where's the steel going? Where's the wood going? And we're saying it's possible now, not just to do no harm, but restore the environment to a condition that it can help us regenerate the earth. And we are also talking about you've got to reach out beyond the owner. I'll give you an example. Larry H. Miller, when I was in school here, you guys all know Larry H. Miller, the car dealer. They had a great idea. And they said, look, we've got these car lots all over the place. It rains. We can capture that water. We can wash our cars with it. Why do we use the fresh, treated water to wash our cars? It was a great idea, and they built it. And the state came in and said, you can't do that. That's our water. We own that water. You cannot decide how to use that water. You had to change the laws to make water recycling possible. So the vision of the engineer is that you're a leader, you're a planner, you're an innovator, you take risk and you manage risk, and you are a leader in the public discussions in coming up with your projects. The Code of Ethics of ASCE says you will hold paramount the safety and the health and the welfare of the public and use the sustainable development techniques. This is a quote from Mr. Ray Anderson, who I met many years ago. He was a visionary man who was the CEO for a carpet company, and he was the first one to be concerned about corporate social responsibility. And this is what he said: we are all a part of the continuum of humanity and life. We will have lived our brief span and either helped or hurt that continuum, and the earth that sustains all life, it's that simple. Which will it be? So if you're going to invent the future, the best way to predict it is if we invent it ourselves. That's you guys now. And so remember this quote where we said, the earth is full and there is enough to spare, and yea, I prepared all things. Well, the Lord also said, for I have given unto the children of men to be agents unto themselves. In other words, the world that he gave you is in your hands. You can choose to follow the commandments. You can violate those. You can violate the physical laws. You can do whatever you want. But what I'm telling you is that the earth is not enough unless we care for it. And with that, thank you very, very much for listening.